Hey guys, welcome to another lesson. So today we're going to cover the topic of rates of change, which requires a little bit of differentiation. It's certainly followed on after doing calculus differentiation in year 11. Some schools do in year 12. But now for those that are aware of the old syllabus, so that was about 3 years ago, rates of change used to be taught as part of the applications of calculus topic, which is generally taught towards the end of year 12. But then the new syllabus and the way that NESA has sort of set up the structure for the syllabus, it's normally now thrown into the year 11 syllabus right after calculus, right after differentiation. So today I'm gonna introduce the concepts of differentiating and applying differentiation to rates of change. So we're going to do the classic 3 shapes of the cube, the sphere, and the cone. Right? I mean, they're very textbook. You will see them in most, I reckon most exams either have one of those 3. If there's a few rates of change questions, at least one. And then throughout the next few lessons, we'll cover past paper questions. And for those that do extension 1, I'll cover this concept that called implicit differentiation, where it's a cool little technique to apply to questions that have Pythagoras type applications. Is the most common one. So we'll start with just a general framework on how to do rates of change, and then apply it to the 3 most common shapes. So, I mean, a really good place to start is the common shape formulas. Right? So if I say common shapes, I mean, you guys know your year 8 measurement formulae, but yeah, just in case, right? And the first one is a cube. Now, and the reason why it's important for me to sort of show you these formulae, even though you know it, it's more that most of the questions deal with one of these formulae. So if you have a cube, it's either volume or surface area. Now, the cooler questions, though, combine both. And I'll show you an example. I think it's with the sphere in a few examples time. But obviously, if we have a cube, looking like that, where let's say, for example, the side here, I'll just call it S, for simplicity. I know all these sides are equal, so S. So obviously volume is S cubed, and surface area, let's just use A, is now there's 6 of them, 6 of the square, so 6S squared. Right, pretty. I mean, that's year 8 in nature. Now, then the next most common one, in fact, it's probably the most common one, most common question type is a sphere, right? So we all know that from our year 8 studies, or year 9 for some of you, year 10 for some of you, and the volume of a sphere is 4/3 pi r cubed. Now, I never understood the connection, but it's always seemed to be a bit of too nice to be a coincidence that the derivative of the, if you differentiate this side with respect to r, you actually get the 3 comes down, cancel out the cubed, 4 pi squared. I don't know. Maybe you guys can tell me whether it's a coincidence or not. Google it and let me know in the comments. But yeah, I don't know whether it's a coincidence, but it just happens to be that way now. And last but not least, the cone. Now with a cone, the most common sort of type of question is less about the 2 formula. It's just about volume and something else. And I'll explain that something else in question when I get to it. But the volume is 1/3 pi r squared. And I think I'm just going to leave it there. We don't really need to deal with the surface area. Well, maybe for completeness, I'll just throw it in. Don't really deal with it. So it's always the circle on the bottom, pi squared plus pi r s, where s is a slant height in this case. So maybe I will label the letters. That's s there. That was right angle there. That's height. That's the radius of r. Yep. So that sort of sets us up for the formulae side of some of the questions we're going to apply rates of change to. Now, I think it's very important for us to then say to ourselves, well, what is a rate? I mean, we really haven't, I haven't actually talked about what that is right now, right? So, like whenever you talk about rates back in year 8, when you did rates and ratios, a rate is basically a comparison of 2 quantities, right? So, for example, price of apples might be $5 per apple, right? Dollars and number of apples being the 2 quantities might be, you might go $5 per liter in terms of like juice and stuff like that. But the rate we're really talking about in this topic, right? The definition of a rate, maybe I'll just put that up here. So whenever we talk about the rate of change, right? Yeah. That's really referring to, let's say the rate of change of, let's say a quantity P, right? In mathematics, we basically denote change with the letter D, which is, from the Greek letter delta. Delta often is the letter of change. So then the rate of change of P will be delta or dP over dt. And dt is important because that's change in time. Now, everything that we do in this topic, it's always with respect to time. Yeah. So just to be clear, dP there refers to change in P, while dt there is change in time. So P can be anything from population to volume. If it's a volume, it will be a V. Surface area will be an A, et cetera, et cetera. So that top letter is referring to the rate of change of something, a quantity. But whenever we talk about rate, right, and maybe I'll highlight this here. Whenever you see the word rate, it's something dt, right? dt is what it refers to there. And in this case, P is the quantity that I'm changing. So that's basically all the theory we need to work on to do this topic. So let me set you up with, I think I've got 4 examples prepared. Let's see how far we go. I don't want to make this video too long, but it's good if I do at least 1 question of each for the 3 types of across cube, sphere, and a cone. So let's start with the first one. Right? A few examples. So quite simply, if I said to you a cube is expanding such that its sides are increasing at a rate of, there's a word rate, right? Now, we're going to dig through this. Question 4 centimeters per second. Yep. We're going to dig through this, translate all the key things here into the mathematics, right? So before we do that, let's finish off this question. If the sides of the cube are currently X centimeters. Yeah. How they find the rate at which its volume, there it is, I'll give that an line, is increasing at when X equals 10 centimeters. And exactly, you know what? It's so copy and paste. I'm just literally gonna, I'm gonna copy and paste. And I'm just gonna replace some keywords. Yeah, let's replace volume and maybe replace the 10, right? Where let's call this part B, which is surface area. Hope I can fit that. Just is 8 centimeters, right? It's copy and paste. So let's copy and paste. So guys, that is my my question for the cube application, right? So what you're gonna identify to yourself here, right? Let's highlight it. We're gonna rate the sides are increasing at a rate of 4 centimeters per second. Now, what that's referring to, the very moment you see the word rate, right? It's D something, right? DT is on the bottom. That's what rate is, right? That's what rate is. And then this is a rate that the sides change at. So if I whip up a quick diagram for you, right, of a cube, right, and it's telling me that at any point in time, currently, in fact, the side is X. So before in the formula, I had volume is equal to S cubed. Now it's X cubed, right? Similarly, surface area is 6X squared, right? They're the 2 formulae that I'm working with now. Now in this question, so it goes, the sides are changing, so X is changing. So this fact here, this 4 centimeter, right, is dx dt, right? That's crucial. Identify that to me. Part A says find the rate, right? So we're finding something with a rate, right, that the volume is changing at. So this guy here is telling me I need to find dv dt, right? That's the question. Yeah, so the question in blue gives you that the rate of change for dx dt is 4. The question for part A is asking you to find dv dt, and it's also given you one extra element, right? It's given you that x equals to 10 centimeters at a point in time, right? Yeah, so we got the x dt equals to 4, we got x equals to 10, and it's asking us for dv dt. Now, so what I'm going to do for part A, I'm going to access this question, this formula here, v equals to x cubed, right? You know what? I'm just going to remove, because I'm doing this for part A, let me remove the surface area. Let's get rid of this box. Now, I wonder if you guys are okay with this. Normally, right, if x is subject, normally back in calculus, I would say this is equal to, if I differentiate it with respect to x, what happens, guys? The power goes down squared, right? And you're done, kaput, done. Now, I don't want, the questions are not asking me for dv dx. It's asking me for dv dt, right? It's asking for dv dt. So what do? This is what I do, right? I'm going to do something that, you know, some teachers call it chain rule. Some people don't give it a name, but basically if I have v equals to x cubed as my starting formula for volume, and I want dv dt, this is what I'm going to do, right? Actually, can I put dt, just to demonstrate point, I'm going to put it in a different color, right? dt, yeah? Now, I know dv dx is this, right? That's how I used to differentiate with respect to x. So this is what I'm going to do. To get dv dt, I'm going to go dv dt is equal to dv dx, right? Which is what I have, multiplied by dx, and then dt there, the new dt. Can you see what happens here is that the dx, I introduced it, I split the fraction. I mean, theoretically it cancels out to get dv dt, right? Yeah, so all I've done is basically split dv dt, which is what I want, right? That's what I want in the question. Why did I do that? Because now I'm able to substitute this guy into dv dx over here, yeah? So what you get algebraically is therefore dv dt equals to 3x squared multiplied by dx dt, yeah? So the rate of change of v, the rate of change of volume is equal to 3x squared times the rate of change of x. Now, that's cool because using the information in the question, I know x is 10, right? That's given by this fact over here. I know dx dt, the change in the sides is 4, right? That's given by this fact over here. And then I just sub it in, right? I sub it in and I got 3 times 10 squared times 4. Yeah, pretty easy. And if you did that 12 times 100, that's 1200. Now, what's my standard? This is change in volume, right? Change in volume. So, and it's a rate. So I know it's something per second. What's that something? We're talking centimeters and we're talking volume. So it'll be centimeters cubed per second. And that's my answer. Does that make sense? Now, to do it quickly, right? I mean, this step here, right? This step here is basically to show you the chain rule, right? What I say to my students, right? Really, you basically, to do all this in, you know, one step, right? You basically go v equals to x cubed. Whenever you want a rate, whenever you're differentiating, and this is really key, right? Whenever you're differentiating with respect to t, and the formula over here is in terms of another letter, all you got to do is differentiate it like you normally would, bring down the 3, minus 1 to the power. And because this was a different letter, we're just going to multiply that by dxet to work that chain rule in there. That's this bit here, right? dxet. Yeah. So that's the process for me to do. I'm just going to remove that going forwards, right? So for part B, I'll do it the quick way and I'll explain that when I do it. So part B, find the rate at which the surface area change. So this is all you got to do. You say to yourself, well, the surface area equals to 6x squared, right? We know that, pretty easy. Yeah, that's a U rate formula. And then what I do immediately, I want to differentiate this guy with respect to time. Right? I want the rate. Yeah. So just to be clear, I'll go back up to the question. I'll highlight that and say to myself, well, that the rate of change of the surface area is dA dt. Oh, also, guys, there's a different x value, right? At a different x value. Yep, so x equals 8 there. Highlight that. X equals 8. Right, this guy's question mark. All right. So my question's asking for dA dt. That's this guy. So I'm gonna, now what's really important here is that I'm differentiating with respect to time. That expression there has x. So I'm going to differentiate this guy as I always would. So that's 12x. And then multiply that by dx dt to demonstrate that I need this guy in there, right? Yeah, because I don't have a formula that's in terms of t. So when I differentiate it with respect to t, I need to hack on the dt dx. Once you do that, life is easy because x in this case is 8. And I know from the question dx dt was 4. So then sub those in, 12 times 8 times 4 on your calculator. What's that, guys? 3, 8, 4. Now this area, centimeters squared per second. What do you reckon? Not too bad. Not too bad. Let's move on, yeah? So that is a very simplistic question relating to the cube, right? We're now going to do a very similar question with regards to a sphere. Yeah? So with regards to a sphere, let's put it in context of a spherical balloon. So example, yeah? A spherical balloon was filled such that its radius, spelled radius wrong, radius was increasing at a rate of, oh, there's a word rate, a rate of 6 millimeters per second, right? When the radius was 24 millimeters, find the rate that its volume is increasing at. Same as before, right? B, its surface area is increasing it. All right. You know what? For this, maybe we'll do both in terms of 1 dp, right? Round it off to 1 decimal place. All right. So this question very similar. Now let's highlight the things we know. It's a sphere, right? That's important, yeah. Its radius is increasing at a rate of this. Its radius. So what does that represent? Yeah. What does this guy represent? That is, it's a rate. So it's dt. It's a rate that the rate, so dr dt, right? So let me get rid of that. Let me write that better. Dr dt is 6, right? Know that when the radius was 24, ooh, yeah, radius was 24. So that tells me r is 24. Yeah, find the rate. So what I'm finding is a rate that the volume is increasing, rate that the surface area is increasing at. So for part A, it wants dv dt. That is what it wants. Part B, what it wants is dA dt. Right? That's what's missing. So you can see volume, surface area, very common questions, right? Very, very common questions. So the way I'm going to do this, well, I'll draw myself a sphere, and I'll start with the volume being 4/3 pi r cubed. Yeah, start there. Now, please keep in mind that pi is constant. So when I differentiate, it just multiplies with whatever constants that come down, etc. Now, here we go again. We're going to use the quicker way of doing it. Forget about the chain rule, right? Let's just do it. I know when I want the rate of change of v, I'm going to differentiate this guy with respect to time. So time's on the bottom. And when I do that, the variable right now is r. So the moment I differentiate, I know I need to hack on a dr dt on the back, right? So guys, bring down the 3. The 3 multiplies with the 3 downstairs and becomes 4 pi r squared minus 1 to the power, and then times dr dt. Now, why do I need to do this again? Because the letter that I'm differentiating is different to the letter on the other side. Yeah. Now, for those that have always had y equals to something x and dy dx, you've never had this fraction. It's because the letter that you're differentiating with respect to is the expression of the function itself, right? So in this case, it's not dr dt. Now, once you get there, life is easy. All right, let's scroll back up to what we're given. I know that r is 24, and I know that dr dt is 6. So this guy is 6, r is 24. You just plug that in the calculator. I mean, I'll go vertically so I have space to do it horizontally for the next question. 4 times pi times 24 squared times 6 on your calculator. So if you punch that in, I think it's 43,429.4. Let me know in the comments if I make any mistakes, yeah? I think some of you in previous videos have, and I do it quite often. So let me know, guys, that's the answer. But the concept is there, right? You have an expression using measurement from year 8, in this case, volume equals to 4 over 3 pi r cubed. Differentiate, but then you got to hack on the dr dt, right? Because it's we're differentiating with respect to time. Just keep it in mind. Now, part B, same concept, different formula. The surface area of a sphere is 4 pi r squared. Like I said, I don't know what the link is between the derivative of volume and this guy. Is it a coincidence? Don't think so. Don't know. Someone Google it. Let me know in the comments. Guys, that's the formula that I start with. I want to differentiate this guy. I want the rate of change of surface area. So dA dt, bring down the 2, and then multiply that by dr dt. Can you see, the moment you sort of appreciate that when you're differentiating with respect to time, you use a hack on the dr dt on the back, life is easy, yeah? You go through this quite quickly now. And then all you got to do, sub in the stuff you did before, right? There's only two things that are missing. R is 24 and dr dt is 6. Yeah, so then you get 8 pi 24 6. What's that goes? So punch it in the calculator, 3619.1 millimeters area, so squared per second. Is that okay? So cube, pretty straightforward. Sphere, the hardest thing is things like the pi throws people off. A pi is constant. Once you get that, I mean, pretty straightforward. Yeah? So if that's okay, guys, I'm going to do one more question, and that's on the cone, right? The cone has a little bit of a trick, and you'll see why. And this is, I guess, quite fundamental to a lot of applications of calculus questions, especially for those that want to do maximum and minima. Now, if you want to do maximum and minima, I've got some videos already on my channel. Go look at those, because the concept is the same when there's 2 variables at play, right? So I'll show you what I mean. Let's do one more example for this video. Yeah, last example for this video. So example, water is poured into an inverted conical vase with radius, keeps doing radius 9 meter vase. Okay, This is like one of those sculptures, and 12 meter and height. Big vase, height of 12 meters. Jesus Christ. It's almost a building. At a rate of 3.6 meters cubed per second. Now, this is quite interesting, right? Just while you're doing that, think about what is that rate? That's the rate that the water is poured into. And what that means is that, I mean, water being poured into a vase is measured not by the height or the radius in this case, or see that cubed, meters cubed? It's measuring the capacity or the volume of the water as it fills the cone, right? So just keep that in mind, yeah? Because that tells you, I'm going to ask you later, quickly, probably rhetorically, what that rate is. Yeah? If the radius, keep saying radius wrong. If the radius and height of the current water levels are R and H respectively, comma, and I'll draw a diagram for this, right? Show that the volume is given by V equals to 409 pi r cubed. Now, you've never seen a volume of a cone written like that before, right? It was a bit weird. Yeah, once again, I'll ask rhetorically what you think the differences are, but let's get there in a second. Part B, find the rate at which the radius is increasing at when R equals to 2.4 meters. All right, let's zoom out for a bit now. So water is poured into a inverted conical vase. So let me draw a diagram, right? So for part A inverted, so upside down vase, that's a cone shape, looks like that, yep. Now, what do I know about the cone? I know that the radius of the cone is 9 meters. And I know that the height of the cone is 12 meters. What I also know is that at a certain point, the current water levels, right? If you keep filling it in water, is going to be, it's going to have a radius of R and a height of H, right? That's what I know so far. So this is where the most difficult thing, just like maximum minimum stuff, is that I know if I wanted to find the volume of this water, right? The volume of this water at any point in time, the volume of a cone is 1/3 pi r squared times h. Now, this is important. See that formula there? That's what I know from year 8. See that formula in part A? That's different. There are 2 key things that are different. One, the 4/9 is different to 1/3, absolutely. But that's not the biggest part. The biggest part that's different is that my formula from year 8, the one in blue over there, has a h, this one doesn't. That's important. So if you look at the maximum and minimum videos that I've uploaded on my channel, one of the key things is whenever you have a volume formula, that's 2 letters, right? In 2-unit advanced maths, or 3-unit extension 1 maths for that matter, whenever you have 2 letters, it doesn't really work with calculus, right? They want 1 letter, 1 variable. So what does that mean? It means somewhere in this diagram, there's going to be information where I can make h the subject in terms of r, and then sub in h, and then no more h's, right? And then I should get what I want. So the question at play here is, where's the information in the diagram that lets me make h a subject? And for those that know, right, you can see, right? Can you see similar triangles at play? Right, similar triangles at play. there it is, right? Where you got 9 over here, 12 over here. So big radius is 9, big height is 12, small radius is R, little height is H. So, if I was to sort of redraw that similar triangle here and actually isolate the numbers, so that's R and that's H, and that's 9 and that is 12, right? So using similar triangles, right? Small on large, R on 9 equals to H on 12. Now, depending on the question, sometimes a question has no H's. In this case, no H's, right? So I make H a subject here, times the 12 up. Simplify that, what's that? 4 and 3. Sometimes a question might have no R's, right? It's all in terms of H, in which case you do the opposite, right? Just be flexible with that. So once you get that, I'm going to sub that. Right, I'm going to sub this guy here, plug that into this guy here, and I say, therefore, volume is a third pi r squared, and now multiplied by 4r on 3. Yeah, the 3 times the 3 becomes 9 on the bottom, 4, and then the r cubed. So therefore, volume is 4 on 9 pi r cubed, right? And that is a good start, right? That's a good start. I haven't done any rates yet. Can I ask a favor? I'm going to, can I fit? No, I can't fit. I'll just do the next page. But before I do it, what are we given? Right, the 9 and the 12, I've used it to derive my pink similar triangles. But now the rate I haven't used. The rate, what's that? That the water is poured in, right? So I told you before, you can tell by the units, that guy there looks like that is the rate of change of volume is 3.6, right? That's important. Now, what else do I know in this question? I've got the rate of change of volume. What am I finding for part B? Part B, find the rate at which the radius is increasing at. So part B is asking me to find the radius increasing rate. That's dr dt question mark. And it also tells me that r equals to 2.4, right? They're the information I need. So I'm going to use the formula for part A, and I'm going to differentiate it with respect to time and then solve it. So let me go over to our next slide and do it here, right? So for part B, I know from part A, volume is 4 on 9 pi r cubed. Guys, differentiate this guy with respect to time. So dv dt equals to, bring down the 3, multiply or cancel out with 9 to get 4 on 3 pi r squared. And then, of course, I'm differentiating with respect to time. That's in terms of r, times that by dr dt. Yeah, that is differentiating with respect to time, right? So what do I know again? I know dv in this question, dv dt, what's that? 3.6, 3.6. And I know that the radius right now for this question is 2.4. This is what I need. So I'm going to make this green part the subject. Yeah, I'm going to sub everything in and then chuck all the stuff over to the other side and leave the green by itself, right? So I've got 3.6 equals to 4 over 3 pi 2.4 squared times dr dt. Yeah, chuck this part here. Oops. Chuck this part here over the fence, right, to isolate dr dt. Now I'm just going to write it like this, divided by 4 on 3 pi times 2.4 squared. Punch in the calculator, 1 dp, I think it's 0.1 meters per second. Does that make sense? So hopefully that gave you a bit of an introduction on rates, where it's all about something over dt. If they're asking for volume, dv dt, surface area, dA dt. If they're asking for the radius, dr dt, etc., etc. So 3 examples touching on 3 common shapes. In the next few lessons, I'll touch on past paper questions, and in the last lesson, I'm going to show you how to do some sort of Pythagorean applications where you can do it by making, you can do it by making the letters subject, right? And then doing it like you do here, or you can use implicit differentiation. So I'll leave it there. Thank you very much. If you like this video, please give me a like, right? It helps with the search engine for people trying to find these videos, and also subscribe to my channel. Let your friends know. Cheers. Thank you.